All right, hello everyone. So today we're going to talk about the central limit theorem for sample means. But before we talk about that, we need to talk about let's see, think. Sampling distributions. Okay, so what is a sampling distribution? Okay, we now consider the concept of a sampling distribution of a statistic. All right, and what does this mean? So instead of working with values from the original population, we want to focus on the values of statistics. Remember what a statistic is? That's some sort of quantity that describes the sample, such as sample proportions, how much of the sample was female, how much was male, that's a proportion, or the mean of a sample. What's the average height of the sample, of the sampled individuals, stuff like that. We are talking about these statistics that come from samples, and they're obtained from the population. Okay, so we want to do that, and the way we're going to do it is we're going to discuss sampling distributions for statistics. That right there is the big main, that's the object of study for this section. And then we are going to look at sampling distributions for proportions and means. And each sampling, statistic really has its own sort of sampling distribution. And so if we're just going to look at the first two, which is proportions and means. And in fact, that's all we're going to really look at. We will see a little bit the sampling proportion of the variance, but we will not be expected to know that one. Okay, so sampling distributions of a statistic. Well, what is it? Okay, so you have a random variable x, right? And this could represent a particular person sampled from a population. And then what you have is you take n samples of that random variable. So that would be like n people from a particular population. And we collect this sample of size n. And what you can do is you can then take the mean, say, and you get this mean here. And each one of these is a copy of this random variable, so long as we sample independently, which we almost always do. This now is a new random variable. This mean, this x bar, is a new random variable. It is also a statistic, right? Because it's a characteristic of a sample. Statistic. It is also a statistic of the sample of size n. What is the distribution of this new random variable? That is what we call the sampling distribution. Okay, so you take a sample, and that gives and you take the mean of that sample, and that's a random variable. The question is how is that random variable distributed? That is the sampling distribution of the mean. We're going to talk about how it's distributed, but for now we're just looking at what type of object it is, and that's what the sampling distribution of the mean is. Okay, now there's another type of statistic that we would like to take the sampling distribution of, and that is a proportion. And this is surprisingly useful. It comes up an awful lot. So again, you have a random variable x, and then you sample x n times. And then you take a proportion, right, which is the number of xi with a certain property. Is xi, is your sample from the population, is it a male or a female? What proportion is male? Are they over 5 feet or are they under 5? What proportion is over 5 feet? So that's the proportion. It is a statistic. This p hat, that's called p hat with that little hat over it, that is a new random variable. And it is going to have its own sampling distribution. And we are going to be able to study that sampling distribution and compute probabilities regarding it. So how likely is it that a sample of 50 persons were more than half, were 60% male? What's the population? What's the probability that a sample of 50 persons, 50 people, is 60% male? That's the probability we're going to be able to get. Okay, what do we have here? So this is also a statistic. Statistic. All right, and what distribution does this new random variable has? Well, whatever it is, it's going to be called the sampling distribution of the proportion. All right, and that's what we're going to be studying. Okay, so what does this even look like? So the general behavior of a sampling distribution. So remember our proportions. We've got this, we have got this population, and we sample from it once, 2, 3 times, all of them of the same sample size n. And we're just going to sample from it. And we're going to do it many, many times, more than 3. So many. That, and we're going to get a whole bunch of different percentages. Those different percentages form a distribution. And as it turns out, as remarkable as it may seem, that distribution of those proportions of samples is going to be a normal distribution. See, so let's just pretend that we've got a population of people, and I sample 10 of them. And so the proportion of male to female might be 70%, right? So that one would be 0.7. And then another one I get is 0.7. But the other one I get is actually 0.3. There was only 3 males out of the 10. This is random because it depends on the random sampling, and each proportion is going to be a number. And so those random numbers have a proportion, have a distribution. And as it turns out, that is a normal distribution. And so because it's a normal distribution, we can compute probabilities. What's the probability that given a certain population, what's the probability that when I sample 10 individuals, I get 3 females? Now, some of you might recognize that as being a binomial distribution problem. And you're absolutely right. It is a binomial distribution problem. But when the sample size is large, it'll be more convenient to think of that as a normal distribution rather than a binomial distribution. Okay. General behavior of sampling distributions. Okay, so that one that we just saw was proportions. And now what we're looking at are the means of a sample. So I, again, sample so many n from my population, and I compute the average of that population, of that sample. And I get these different numbers. And I just do this a bunch of times. If I do this enough times, and I compute the probability distribution of that random variable, x bar, I'm going to get something that is not exactly normal distribution, but it tends towards a normal distribution. We'll discuss more about that. When the sample size is small, it's more like a student t distribution. Well, what's that? Well, we'll find out. But as n gets large, that distribution approaches a normal distribution. And that means we can do probability on it. And that probability is going to be super important in hypothesis testing. Okay, this is one you don't need to pay too much attention about, but the idea is if I have a bunch of samples and I take the sample variances, right, the variance of each sample, they actually do not make a normal distribution. They make this skewed distribution. This is actually called a chi-square distribution. Isn't that interesting, right? Well, we don't need to know too much about that. We're not going to be discussing that in the interest of time throughout the course. Okay, so sampling distribution of a statistic. The sampling distribution of a statistic. The sampling distribution of a statistic, such as a sample proportion, Come on, there. Proportion or mean is the distribution of all values of the statistic when all possible samples of the sample size n are taken from the same population. That's important. The sampling distribution of a statistic is typically represented as a probability distribution in the format of a probability histogram. That's very true. We commonly see that as a histogram, sometimes as a formula and sometimes still as a table, and we'll see that, but generally a histogram. Okay, sampling distribution of the sample proportion. So right now we're going to spend just a few slides talking about the proportion, and then we're going to talk about the mean after that. Sampling distribution of the sample proportion. The sampling distribution of the sample proportion is the distribution of sample proportion or the distribution of the random variable p hat, which is an estimated, the hat refers to as an estimated. So this is a proportion statistic. I think next time I teach this, I really need to introduce this a lot sooner. When we talk about statistics, I should introduce the sample proportion. Okay, with all samples having the same sample size n taken from the sample population. All right, so same sample size n, and it's the proportion. Okay, some notation for proportion. We need to distinguish between the population parameter proportion and the sample statistic proportion. So this is the population proportion. This is a parameter of the population. This is a statistic. We just use the hat, pronounced p hat, when symbols are used above a letter, such as x bar, p hat. They represent statistics and not parameters. Remember, parameters are usually written in Greek letters. Sigma is the sample standard deviation. Mu is the sample. Sigma is the population standard deviation. Mu is the population mean, and sometimes eta is used for the population median. And those are all Greek letters for population, for parameters. Okay, behavior of sample proportion. The distribution of sample proportions tends to approximate a normal distribution. Sample proportions target the value of the population proportion in the sense that the mean of all the sample proportions, p hat, is equal to the population proportion. Okay, so the expected value of the sample proportion is equal to the population proportion. So if we regard p hat as a random variable, we can compute the average, the mu, the average of that random variable. And as it turns out, the average of that random variable equals p, the population proportion. The mean of all sample proportions, mu p hat, is equal to the population proportion p. So that is what I'm talking about. That's what that means. So the expected value of the sample proportion is equal to the population proportion. Okay, an example. All right, so you are free to skip these blue slides. In the video, there'll be chapters. I'll put in chapters on YouTube, and you can feel free to skip to the next little chapter in the YouTube video. All right, the blue slides are not graded necessarily, though I do look at them, but they're not graded. All right, consider repeating this process. Roll a die 5 times and find the proportion of odd numbers. What do we know about the behavior of all sample proportions that are generated as this process continues indefinitely? All right, so what do we know about the behavior of all sample proportions that are generated as the process continues indefinitely? All right, so this right here is going to be my sample proportion p hat, and this is going to be the probability of getting that p hat. So I'm really just treating this p hat, this proportion of my sample of 5 dice roll, as a random variable. Okay, well, what are my possible proportions, right? I've got 5 dice. What are my possible proportions? I could have 0 are odd, right? 0 are odd. What's the probability of 0 being odd? That means that they're all even. And so this right here, to calculate this, I use a binomial random variable. So this is going to be binom dot dist 0, because that's the number I'm interested in. 0, the n is, the trials is 5, the p is 1/2. 1/2 because the probability of my single roll being odd or even is 1/2. And then this is going to be 0 because I'm not looking at accumulating these probabilities. And so I need that value there. Okay, let me go ahead and make this proportion using Excel. I'm going to go to Excel. Okay. Let's open up a new, can I open up a new, I'll just open up a new sheet here. Oh, mercy, what's this not? Okay, sheet. All right, great, here we go. All right, so I've got 5 dice roll. All right, so this will be p hat, and then this here will be p of p hat. Okay, so p hat could be 0. I could have just 1. I could have no evens, or I could have 1 out of 5 be even. January, no. 1 out of 5 be even, or, oh no. Oh, that's bad. All right, 1 out of 5 be even. Or I could have 2 out of 5. 2 out of 5 be even. Good, that's better. Or 3 out of 5. Let me just fill. Oh dear. Okay, 0. Okay, 2 out of 5. Enter. 3 out of 5. 4 out of 5. And then 5 out of 5. Okay, so those are all my possible. So those are all my possible outcomes here. Number, enter. Okay, great. Decrease. All right, there. So there's that. So there's all my possible outcomes. Now what I'm going to do is I'm going to equals, and then the probability of this is going to be binom dot dis times, okay, number of successes. Number of successes is going to be this thing times 5, because it was a proportion. I divided by 5, and I want to get the number of successes, so I'm going to multiply by 5. The trials was 5 trials, and the probability of success is 0.5. Cumulative, no thank you. All right, enter. Okay, there's that. Now I'm going to copy, Command C. I'm going to drag, Command V. And there it is. Okay, so there are my probabilities that I found using the binomial distribution. So let's just go ahead and use that. Actually, I wonder if I could screenshot that and share to Notability. Add to existing note. This one. Oh dear, is it just gonna put it at the end? Import. Open. I'll bet it just put it at the end. Lovely. Alright. Cut. Okay, there we go. Good enough. Okay, right here. Paste. Paste, thank you. All right, can I crop? Crop. Oh, is that crop? Crop. Okay. Good. Good. Can I make it bigger? All right. Okay. Anyway, yeah, there it is. Go ahead and erase that writing. Oh, actually, I'll just kind of go like that. Oh, it didn't. Okay. It's good enough. All right. So there's my probability distribution. Okay. So what do I need to do with that? So consider that ruled out. What do we know about the behavior of all sample proportions that are generated as this process continues indefinitely? Okay. So anyway, so that's how we compute the probability distribution for p hat. And if you were to plot it, you would get this. So that distribution, and notice it somewhat resembles the normal distribution. Now we found these probabilities theoretically using a binomial distribution. But what you could do is discover the distribution empirically using 10,000 rolls. Well, that would be what? 50,000 rolls. But you do the 5 rolls 10,000 times. Use a computer to do that. And you get an empirical distribution. Okay, great. Now let's talk about sample mean. So sampling distribution of the sample mean. Sampling distribution of the sample mean. The sampling distribution of the sample mean is the distribution of all possible sample means, or the distribution of the variable x hat, with all samples having the same sample size n, taken from the sample population. Okay, behavior of the sample mean. The distribution of sample means tends to be a normal distribution. This will be discussed further in the following section, but the distribution tends to become closer to a normal distribution as the sample size increases. So, strictly speaking, it's not a normal distribution, but it gets closer and closer to it. The sample means target the value of the population mean. That is, the mean is the mean of the sample means is the population mean. A lot of mean going on there. The idea here is that so you've got x hat is the random variable. That's the sample mean. The mean, the population mean of our random variable ends up equaling the sample mean, or not the sample mean, the population mean of x, of our original random variable. And so that's what we mean by this statement. Okay, let's take an example. So consider repeating this process. Roll a die 5 times to randomly select 5 values from the population, 1, 2, 3, 4, 5, with replacement, of course. Then find the mean x of the results. What do we know about the behavior of all sample means that are generated as this process continues indefinitely? Okay, and so this probability is a bit more difficult to compute. We could do it, but in the interest of time, we'll just scroll down here and see what the answer would be. So, we randomly generate 5 numbers between 1 and 6, and we compute the mean of those 5 numbers. We get numbers like these, 3.4, 4.4, 2.8, and if we were to repeat this experiment 10,000 times, we would get 10,000 different numbers. If we made a histogram of those numbers, it would look something like this. And notice how well this approximates the bell curve of the normal distribution. So that's what we're talking about. The mean, the sample mean, the mean of my samples has its own normal distribution. Okay, so those are 2 examples. Now here's a 3rd example. All right, so a friend of the author has 3 children with ages 4, 5, and 9. Let's consider the population consisting of 4, 5, and 9. Generally, we don't deal with populations that small. But in the interest of explaining what's going on, we're going to do it. If 2 ages are randomly selected, so 2, so the sample size is going to be 2, is randomly selected with replacement from the population 4, 5, 9, identify the sampling distribution of the sample mean by creating a table representing the probability distribution of the sample mean. Do the values of the sample mean target the value of the population mean? All right, so let's go ahead and do this. So the sample size, the population is 4, 5, 9. And we are going to sample from that very small population with replacement. And we're going to see how many samples. So these are samples of size 2. We're going to get a sample of size 2. We are going to compute its mean. And then we're going to compute the probability of that. All right. So, first I could sample 4, 4. All right, it's 2, sample 4, 4. The mean of that is going to be 4. And the probability of that we will determine later. The next thing I could get if I sampled is I could sample 4, 5. Now, once I do that, I compute the mean to be 4.5. What else could I sample? I could sample 4, 9. And that would have a mean of 13 over 2, which is 6.5. Okay, and that's that. Now I could sample 5, 4, and that would have a mean of 4.5. I could also sample 5, 5. That would have a mean of course, just 5. I could sample 5, 9, and that will have a mean of 7. And then I could sample 9, 4. And that would have a mean of 6.5. I could sample 9, 5, which again has a mean of 7, or I could sample 9, 9, which has a mean of 8. Now, each one of these samples is going to be equally likely. These are all the possible samples I could get out. How many are there? 9, right? 3 groups of 3, 9. So each one of these particular samples has a probability of 1/9. Each one is just equally as likely as the other. So 1/9. So all of these are going to be 1/9. All right. So let me simplify this into a table that just gives me the outcomes. So here's X bar, and the smallest outcome is 4. And that appears just once, so it has a probability of 1/9. Another outcome is 4.5. Now, how many times does 4.5 appear? I see it once, twice, and that's it. And so that's going to have probability of 2 out of 9. The next probability is 5. Which occurs once, so that has a probability of 1/9. The next one is 6.5, which appears twice, so it has a probability of 2/9. And then there is 7, which appears twice, and so that is going to have a probability of 2/9. And then we get, oops, that's not 9. That should be 9, not 8. Should be 9. And then we get 7. Okay, so there's 7. That comes 2 9s. And then there's 9 itself. And that happens 1 in 9 times. So let's just add and make sure that these are all, so that all adds up to 1. This is the sampling distribution of the mean for this population with a sample and a sampling size of 2. If I were to plot this thing, so there'd be 4, 5, let's see now, 4, 5, 6, 7, 8, 9. Okay. So, everything from 4.5 is 1/9. From 4.5 to 5 is 2/9. 5 to 6.5 is 1/9. 6.5 to 7 is 2/9. 7 to 9 is 2/9. And then 9 is 1/9 there. All right, so this is the probability distribution of my very simple experiment with the sample with the population size of only 3. Do the values of the sample target the mean of the population mean? Okay, well, let's investigate that. So the population mean mu equals 4 plus 5 plus 9 all over 3, which equals 6. The mean of my random variable is going to be 4 times the probability of getting 4, which is 1/9, plus 4.5 times the probability of getting 4.5, which is 2/9, plus 5 times 1/9, plus 6.5 times 2/9, plus 7 and 2/9, 7 times 2/9, plus 9 and 1/9. Okay, let's simplify this. That's the same thing as this right here makes 9/9. This here is 9/9. This is 9/9. 13 plus 14 is 27. These two together make 3/9. And so, yeah, this right here makes 14. This one here makes 13 over 9. Together they make 27 over 9, which is the same as 3/9. And so this mean here is actually 6. And so, yes, it does target the population mean. So mu x hat equals 6 equals mu. So these are equal. All right, so there's that example. Okay, now basically we're getting into section 7.2 now, which is on the central limit theorem. All right, let's proceed. So the central limit theorem tells us that the sampling distribution of the mean is a normal distribution. We speculated, or at least it was just told to us that was it. But now we have basically a theorem that tells us that is it. So tells us that the sampling distribution of the mean is a normal distribution. And it gives the mean and variance. So this central limit theorem gives you the mean and variance. So a theorem is basically a statement of truth. And this statement of truth is that if you have a sample mean, the distribution of that sample mean is going to be normally distributed. And it's going to have the mean the same as x, and the standard deviation is going to be the one with the x, but you divide by the square root of n. And this is going to be true under certain circumstances. Notice that there was no claim that x had to be a normal distribution. Okay, this in turn allows us to use a normal distribution for some very meaningful and important applications. Okay, a little rehash here. The central limit theorem. For all samples of the same size n, with n greater than 30, the sampling distribution of x hat, that's the mean, can be approximated by a normal distribution. with mean mu, that is the same mu from the population, and the standard deviation sigma over square root n, which is the same sigma as the sample population, and n, of course, n is the sample size. Okay, practical rules for real application involving a sample means. So there are some requirements in order for the theorem to be valid, and one of the requirements is an either or. Either the population has a normal distribution to begin with, or n is greater than 30. So that means that if it's not a normal distribution to begin with, but n is greater than 30, that's okay. Central limit theorem applies. If n is less than 30, but the original population is normally distributed, that's okay too. The theorem applies. It's when both of these are violated, you have something that is not known to be normal, and n is smaller than 30. That's when you've got to be careful. The central limit theorem may not apply, and the distribution of the sample mean may not be normal. Okay. Or even close to normal. All right. However, if those conditions are met, then the mean of the sampling distribution, of the sampling mean, is going to equal the population mean. The standard deviation of the sampling proportion is going to be related to the population standard deviation divided by the square root of the sample size. Now, if that's the case, if you want to get the z-score, you need to do this. Take your data, which is now an average, subtract the mean, which is the same as the population mean, and then divide by your standard deviation for that random variable. And that's how you find your z-score. Okay, practical rules for real applications involving it. All right, so we discussed that. The distribution of x hat cannot be approximated well by normal distribution, and the methods in this section do not apply. So this is if the original population is not normally distributed and this is less than 30. It's what I said on the previous slide. Okay, so there's these requirement checks. You've got to check that it meets the requirement. When working with the mean from a sample, verify that the normal distribution can be used by confirming that one or the other of these are true, or both. The original population has a normal distribution, or the sample size is bigger than 30. All right, another consideration is to make. You need to ask yourself when you sit down to do a problem like this, you need to say, are they asking me about an individual value, or do I have a mean of a sample? If I have an individual value, then I'm doing what I learned in chapter 6, where I take the z-score, where I compute the z-score by taking the data and subtracting the mean and dividing by the standard deviation. That gives me a z-score. I go to the table, I get my probability that way. Okay, so what do we have here? So when you have an individual value, you do it this way. However, if the data that they give you is the mean from a sample, is the mean from a sample of size n, I've quite forgotten what this is supposed to be. Size n. When working with a mean from a sample of population, when working with a mean for some sample of n values, be sure to use the value of sigma over n square over square root n for the standard deviation of the sample means. And so when I find my z-score for this bit of data, when I'm dealing with a mean, I need to use this formula here. Okay, can we have an example? Okay, not yet. That is soon, though. Notation for the sampling distribution of x bar, sorry. If all possible sample random variable, if all possible simple random samples of size n are selected. Remember, simple random sample is a random sample that is all possible samples are equally likely in your sampling technique. If all possible simple random samples of size n are selected from a population with mean mu and standard deviation sigma, the mean of all sample means is denoted by mu of x bar. That's what we denote it. And the standard deviation of all these sample things is sigma x bar. The mean of these values is going to be the population mean. The standard deviation of these values, are x bar, is going to be sigma over n squared. Note, x of the sample mean, the standard deviation of the sample mean, is sometimes called the standard error of the mean. Standard error of the mean, the standard deviation of the mean. Okay, now here's an interesting example. Safe loading of elevators. The elevator in the car rental building at San Francisco International Airport has a placard stating that the maximum capacity is 4,000 pounds, 27 passengers. This converts to a mean passenger weight of 148 pounds when the elevator is full. So they must have used a mean weight of 148 pounds in order to make these equal. We will assume a worst-case scenario in which the elevator is filled with 27 adult males. Assume that the adult males have weights that are normally distributed with a mean. Assume that adult whales, not just these adult whales, but all of the adult whales, have weights that are normally distributed with a mean of 189 pounds and a standard deviation of 39 pounds. Find the probability that one randomly selected adult male has a weight greater than 48 pounds. Okay, so for A, this is a individual value. This is not a sample mean. And X in this case is 148. Let's see. Randomly selected adult has a weight greater than that. So here's my bell curve. I've got 148. The mean here is 189. The standard deviation is 39. I want to find the probability that the weight is greater than 148, which is, maybe around here, right? And so I want this probability. That's to the right. Okay, well, I'm going to have to subtract because Excel only gives me to the left. So I'm going to do 1 minus norm.dist 148 of 189, 39 pounds, 1. Always true when we're dealing with normal distribution. The cumulative is always true when we're dealing with normal distribution. All right, and well, what does this thing equal? Well, I'll open up Excel. All right, so equals 1 minus norm. Oh, is it not? Come on now. Equals. How do I get it? 1. Okay, that's looking good. equals, still not allowing me to type. Oh, because, okay. Great, all right. Equals, yay, 1 minus norm dot dist 148, 189, 39. I hope these are right. And then 1. Okay, enter. It says name. What's wrong? Oh, norm. Norm is bad. Norm.dist. Yes, that's the one. Enter. Oh, mercy. Come on now. Okay. Oh, man, it's wigging out on me. There's that. Get that. Oh. Okay. All right. Okay. Whew. 85%. So it is 85% the probability of somebody, of an adult male being bigger than 148 pounds is 85%. Well, now that's quite a bit. Okay, B. Find the probability that a sample of 27 randomly selected adult males has a mean weight greater than 148 pounds. A mean weight greater than 148. So mean. So this is the mean of a sample. Okay. All right. So what that means is that I am dealing with X hat. And I know that X hat is normally distributed, and the mean is going to be the same as the population mean, which is 189, right? But the standard deviation is going to be the standard deviation divided by the square root of n. In this case, n is 27. So this is going to be normally distributed with a mean of 189 and a standard deviation of 39 divided by square root 27. And I'm just going to keep it like that so that I don't round. Now, this random variable, I want to know what is the probability that the mean weight is greater than 148. So there's my standard deviation, and 148 is likely to be somewhere around here. I mean, the square root of 27 is 3 square roots of 9. So that's probably something like 15. And so if I divide 39 by 15, this standard deviation is somewhere around 3 or less. And so that means that this distribution, guys, this distribution is very, very tight. It's a very narrow distribution. Okay, anyway, let's compute this probability now. So I go to my Excel. There's it. There we go. Equals, yes. 1 minus, because I want to find something on the right side, by nom, yes, dot dist. Okay, now I need to put in my, it's 148 again, but that's the sample mean, comma, trials, oh, not binom, forgive me, normal dot dis. Oh, I'm just going to clear this whole thing because it's going to, norm, I'm not going to press enter, I'm just going to, won't let me. Too helpful, Excel, too helpful. This thing's going to be the mean, which is the same. This thing here is going to be the standard deviation, 39 divided by square root of 27. 1. Just look at that for a minute. Yeah, it looks good. 1. the probability of the average weight being above 84 is just 1. Let's see now. If I go like that, will it give me, oh, there we go, 0.99999998. So how many, what is that? That is 7 nines. So anyway, that's basically 1, isn't it? So it's practically impossible. So this thing here, which is 1 minus norm dot dist of 148, because that's my data for that sample mean, 189, because the mean of the sample mean is the same as the mean of the population, divided by 39 over square root 27, because the new standard deviation is the old standard deviation divided by the square root of the sample size. And then 1, because I'm dealing with normal distribution. And this thing here is basically 1. 1, 2, 3, 4, 5, 6, 7, 7, 7. All right, so that is so close to being 1. You can't, it's just, why would they write something like that? That 27 is, it really needs to be a bit less, quite a bit less. Okay. I don't even know how you could fit 27 people in a single elevator. I mean, that would have to be 5 by 5 and then 2 extra. Maybe that's possible. I don't know. All right, interpretation. There is is that the number we got? Yeah, 85.43 probability that an individual will weigh more than 180 pounds. So that's not terribly unlikely. I mean, that's not terribly likely. And there is a terribly likely, right, probability that 27 randomly selected males will have a mean weight of more than 148 pounds. Given that the safe capacity of the elevator is 4,000 pounds, it is almost certain that it will be overweight if it is filled with 27 randomly selected adult males. Almost certain. Okay, just one more white slide before, and then the rest is just a bunch of examples. So identifying significant results with probability. So the rare event rule. All right, so significance. So this is super important. So significance. Identifying significance. If under a given assumption, so someone is assuming something, and if they use that assumption to compute a probability of a particular observed event is very small, and the observed event occurs significantly less than the significantly greater than what we typically expect with that assumption, okay? So if an observation is significantly less or significantly greater than what we would expect given the observation, we conclude that the assumption is, what did I put here? Is probably not valid, I think is what we need to put. Why is that so small? Okay. Probably not valid. Okay, example. Somebody tells me that unicorns are super, super rare. I go outside. I observe. I look outside, I see a unicorn. Let's see, is that appropriate here? I see a unicorn. And given the, okay, now, stay with me now. So the assumption is that a unicorn sighting is extremely rare. I step outside and I see a unicorn. And the probability of me seeing a unicorn, given that unicorns are extremely rare, is very, very small. And so, if the probability of a particular observed event is very small, and the observed event occurs significantly less or significantly greater than expected, my sighting of a unicorn was significantly greater than expected, given the assumption. I would then conclude that the assumption is probably not true and unicorns aren't terribly rare. Or maybe somebody said, horses are extremely rare, and I go outside and I see a horse. That was a significantly, the probability of that was let's see, the observed occurrence, so that occurrence occurred significantly greater than expected. And so I'm going to go ahead and reject that assumption that horses are rare. Okay, I believe the rest is just a bunch of examples. Yeah, okay, so you can end here if you are not interested in examples. But if you are, stay tuned. Okay, body temperature. Assume that the population of the human body temperature has a mean of 98.6 degrees Fahrenheit, as is commonly believed. Also assume that the population's standard deviation is 0.62 degrees Fahrenheit, based on data from University of Maryland researchers. If a sample size of n equals 106 is randomly selected, find the probability of getting a mean of 98.2 or lower. Okay, so what's the probability of getting a mean? A mean of my sample size, right? So I am dealing with x hat. I am not dealing with an individual value. I'm dealing with x hat because I am talking about find the probability of getting a mean. With that sample, find the probability of getting a mean. Okay, so let me look. Is n greater than 30? Yes. Yes, it is, because n equals 106. So that means that x hat, so x hat is normally distributed with mu of x hat equaling the same mu, the same mean, so that's 98.6 degrees, and the sigma of my sample mean is going to be the standard deviation of that sample mean divided by square root of 106. So there's my mean, there's my standard deviation. This is my, 98.2 is my data point. And now I'm going to find the probability. What's it say? Find the probability of getting a mean of that or lower. Okay, so that's to the left. So I draw my, so here's 98.6. And here is 0.62 divided by 108. So that's like 0.06. So again, that's extremely tight. That's a very tight distribution. Okay, so this is like 0.062 or whatever away. All right, and I've got 98.2. Which is going to be, what is that? That's going to end up being like, I don't know, 8 or 7 or 8 standard deviations below the mean with this particular probability. So let me find I want this. Okay, so let me go ahead and take a, go ahead and go to Excel. Okay, there it is, right there. All right, equals norm dot dist 92.8 degrees. The mean is 98.6. The standard deviation is 0.62 divided by the square root of 106. Oops. Okay. Cumulative true. 0. Very zero, right? There's no, I can't even, yeah, it's very, very zero. All right, so the probability of that, did I say 92.8? Go back. Where's my zero? Oh, I said 92.8. I meant to say 98.2. Okay, so not so much zero, but still very, very small. That is incredibly rare, right? That's the 1 in a trillionth or more or so. So that probability is, here we go. So let's write it down. So that probability is 1.45 times 10 to the negative 11. Very, very small probability. All right. Result. Interpretation. The result shows that if the mean of our body temperature is really 98.6 degrees, as we assumed, then there is an extremely small probability, extremely small indeed, of getting a sample of mean 98.2 degrees Fahrenheit or lower when 106 subjects are randomly selected and their temperature is averaged. University of Maryland researchers did obtain such a sample mean, and after confirming that the sample is sound, you got to be careful, make sure everything was done correctly, there are two feasible explanations here. The population mean really is 98.6, and their sample represents a chance event that is extremely rare. So there's that. Or the population mean is actually lower than the assumed value of 98.6 degrees. And so their sample is typical. Now, why would their sample not be more or less typical, right? Because the probability is so low, it is more reasonable to conclude that the population mean is lower than 98.6 degrees Fahrenheit. In reality, it appears that the true mean body temperature is closer to 98.2. In fact, my body temperature is usually around 97.6. That's when I take my temperature, that's usually what I get. And so I don't know how rare or what that is, but it is definitely closer to 98.2 than 98.6. Okay. So the central limit theorem. An unknown distribution has a mean of 90. So here's another example. An unknown distribution has a mean of 90 and a sample standard deviation of 15. Samples of size n equals 36 are drawn randomly from the population. Find the probability that the sample mean is between, so this is a sample mean, so I'm dealing with x bar. So x bar is going to be normally distributed with the mean is going to be the same as the sample, 90, and the standard deviation is going to be 15 divided by the square root of 36. That's my standard deviation here. So that's going to give me n 90, 15 over 6. Okay, so, and I want to find the probability that the sample mean is between 85 and 92. All right, let me set that up then. Here I go. I go here. I'm going to go get my keyboard out. Equals norm dot dist, okay, 92, I believe it was 85 and 92. So this is 92, 90, 15 divided by 6 is my standard deviation, and always 1, minus norm dot dist, 85, I think, 90, same thing here. Okay, let me back up. 90, comma, 15 over 6, 1, enter. All right, 76%. Did I get those right? Yeah, 85 and 92. I'll be darned. So the probability of x bar being between these two values is 76%. At least I think that was 76%. Yeah, 76.5%. Okay. Done. That's the probability. Next question, please. This is all the same. Find the value that is 2 standard deviations above the expected value that of the sample mean. All right, well, that's easy enough. That's going to be 90 plus twice the standard deviation of the sample mean, which is going to be 90 plus 2 times 15 over square root of 36. And so that's going to equal 90 plus 30 over 6, which equals 95. So there it is. Find the value that is 2 standard deviations above the expected mean. So that's 95. So that's 2 standard deviations. Before, on the original distribution, 2 standard deviations is 120. That's 2 standard deviations. Notice these sample means are much tighter, much more tightly distributed than the original. Okay, here's another example. The length of time in hours it takes an over 40 group of people to play one soccer match is normally distributed with a mean of 2 hours. That's a weird question. To play one soccer match is normal. I guess they play till 3 or something. Or I don't know what they... to play one soccer match is normally distributed with a mean of 2 hours and a standard deviation of 0.5 hours. A sample of size n equals 50 is drawn randomly from the population. From the population of what? The population of games, the length of time in hours it takes. So it takes an over 40 group. So sample 50 games. The sample size of n equals 50 is drawn randomly from the population. Find the probability that the sample mean is between 1.8 hours and 2.3 hours. Okay, well, so there's my mean. The mean of a sample of 50 games. Well, this thing is going to be, by the central limit theorem, it's going to be normally distributed. The mean is going to be the same. which is 2 hours. The standard deviation, however, is going to be the standard deviation of the population of all games divided by the square root of 50. All right, so let's do that. I've got to go between 2.3 and 101.8 hours. That one. All right. So this is going to be equals norm dot dist. Mercy, I just went blank. 2.3. 2.3. Okay, comma, what's the mean? The mean is 2 hours. What's the standard deviation? 0.5 divided by square root of 50, comma, 1 cumulative always, minus norm dot dist 1.8 to 0.5 divided by square root of 50, comma, 1, enter. 99.7%. So the probability that the average of we have 50 games and we average their time, the probability of that average being between 108 and 2.3 is 99.7%. All right, pretty much, okay, great. Example 8, last example. Okay, here we go. In a recent study reported on October 29th, 12 years ago, on the Flurry blog, the mean age of tablet users is 34. Suppose the standard deviation is 15 years. Take a sample size of 100. Beautiful. That's very easy to take the square root of. What are the mean and standard deviation of the sample means of the age of a tablet? Okay, well, it's easy. The sample mean is going to be exactly the same, 34. The standard deviation of 15 years, standard deviation is going to be 15 divided by square root of the sample size. And so that's going to be an mean of 34 and sample size of 1.5, much more tightly distributed. What's it asking for? What's the mean and standard deviation? So mean of the sampling mean is going to be 34. The standard deviation of that is going to be 1.5. Great. All right. In a recent study, this is all the same. What does the distribution look like? It is a normal bell curve. Since n is greater than 30. Find the probability that the sample mean age is more than 30 years. This here is 34. Here's 30. So if I take a sample of 100 users and I add I find the average of their age. What's the probability that that average age is going to be more than 30? All right, this is going to be a 1 minus norm dot dist. 1 minus because I'm looking at the right. 1 minus norm dot dist times 34. Standard deviation of 1.5. Wait a minute. This is Oops. That wasn't worth it. Okay. Oh, gosh. Let's erase that. Okay. So this is going to be 1 minus norm dot dist of 30, mean of 34, standard deviation of 1.5, and I want it to be cumulative. Okay, so let's take a look at that. See what that is. Go to Excel. Okay, equals 1 minus norm dot dist 30, 34, 1.5, 1 equals, oh, what did it not like? I put in an extra parenthesis, equals 99.6. That's it, 99.6%. Okay, great. Last slide. Find the 95th percentile of the sample mean age. Okay, yeah, interesting. So, out of many samples, what is the mean that is bigger than 95% of them? So I'm going to do norm dot inv 0.95 because I want to find this value where there's 95% to the left. That's the percentile, 95% to the left. The mean is going to be 34, and the standard deviation is 1.5. This one. Okay. Here we go. Equals norm dot inv. Let's see. What am I supposed to put in? Oh, that's right. 0.95. 0.95 divided by 34 was the mean, right? 34, 1.5. Was 34 the mean? Yes, 30. Yeah, 34 is the mean. Okay. 1 point. Ugh. I wish the arrows. Yeah, there we go. 0.5. 36. Okay. Oh, that's not far at all. That's 95 percentile, and it's only 3, an average of 3, and an average of 2 years. So this right here is 36 years, basically. I should give it one more decimal. I should give it one more decimal than that. 36.5. All right, everybody, have a wonderful day. Thank you for watching, and good luck on the quiz.